to enable their size to change over time. But vectors almost always make up for this with their added flexibility. The task at hand is to expand the feature set of the grep Lite utility. Specifically, we want the ability to store n lines of context around a match. Naturally, there are many ways to implement such a feature. To minimize code complexity, we'll use a two-pass strategy. In the first pass, we'll tag lines that match. During the second pass, we'll collect lines that are within n lines of each of the tags. The code in listing 2.22, available at this location, is the longest you've seen so far. Take your time to digest it. The most confusing syntax in the listing is probably this, which appears on line 15. Vec of usize and string is a vector of vectors, e.g. vec of capital T, where T is a pair of values of type usize and string. Usize and string is a tuple that we'll use to store line numbers along with the text that's a near match. When the needle variable on line 3 is set to 00, the following text is printed to the console. Vec of T performs best when you can provide it with a size hint via vec : with _ capacity. Providing an estimate minimizes the number of times memory will need to be allocated from the OS. Note: when considering this approach in real-life text files, encodings can cause issues. String is guaranteed to be UTF-8. Naively reading in a text file to a string causes errors if invalid bytes are detected. A more robust approach is to read data in as U8, a slice of U8 values. Then decode those bytes with help from your domain knowledge. Section 2.11, including third-party code. Incorporating third-party code is essential to productive Rust programming. Rust's standard library tends to lack many things that other languages provide, like random number generators and regular expression support. That means it's common to incorporate third-party crates into your project. To get your feet wet, let's start with the regex crate. Crates are the name the Rust community uses where others use terms such as package, distribution, or library. The regex crate provides the ability to match regular expressions rather than simply looking for exact matches. To use third-party code, we'll rely on the cargo command line tool. Follow these instructions. 1. Open a command prompt. 2. Move to a scratch directory with cd/tmp, cd %tmp% on MS Windows. 3. Run cargo new grep-lite --vcs none. It produces a short confirmation message. 4. Run cd grep-lite to move into the project directory. 5. Execute cargo add regex @1 to add version 1 of the regex crate as a dependency. This alters the file /tmp/grep-lite/cargo.toml. If cargo add is unavailable for you, see the sidebar 2.2 in section 2.3.4. 6. Run cargo build. You should see output fairly similar to the following begin to appear. Now that you have the crate installed and compiled, let's put it into action. First, we'll support searching for exact matches in listing 2.23. Later, in listing 2.26, the project grows to support regular expressions. Section 2.11.1. Adding support for regular expressions. Regular expressions add great flexibility to the patterns that we are able to search for. The following listing is a copy of an early example that we'll modify. Make sure that you have updated grep-lite/cargo.toml to include regex as a dependency as described in the previous section. Now, Open grep-lite/src/main.rs in a text editor and fill it in with the code in the following listing. The source code for this listing is available in this file. Open a command prompt and move to the root directory of your grep-lite project. Executing cargo run should produce output similar to the following text. Admittedly, the code within listing 2.24 hasn't taken significant advantage of its newfound regular expression capabilities. Hopefully, you'll have the confidence to be able to slot those into some of the more complex examples. Section 2.11.2. Generating the third-party crate documentation locally. Documentation for third-party crates is typically available online. Still, it can be useful to know how to generate a local copy in case the internet fails you. 1. Move to the root of the project directory in a terminal, like this. 2. Execute cargo doc. It will inform you of its progress in the console. Congratulations, you have now created HTML documentation. By opening this in a web browser, also try cargo doc-open from the command line, you'll be able to view the documentation for all the crates that yours depends on. It's also possible to inspect the output directory to take a look at what's available to you. Section 2.11.3. Managing Rust toolchains with Rust Up. Rust Up is another handy command line tool along with Cargo. Where Cargo manages projects, Rust Up manages your Rust installations. Rust Up cares about Rust toolchains and enables you to move between versions of the compiler. This means it's possible to compile your projects for multiple platforms and experiment with nightly features of the compiler while keeping the stable version nearby. Rust Up also simplifies accessing Rust documentation. Typing Rust Up doc opens your web browser to a local copy of Rust's standard library. Section 2.12. Supporting command line arguments. Our program is rapidly increasing its feature count, yet there is no way for any options to be specified. To become an actual utility, grep-lite needs to be able to interact with the world. Sadly, though, Rust has a fairly tight standard library. As with regular expressions, another area with relatively minimalist support is handling command line arguments. A nicer API is available through a third-party crate called Clap, among others. Now that we've seen how to bring in third-party code, let's take advantage of that to enable users of grep-lite to choose their own pattern. We'll get to choosing their own input source in the next section. First, add Clap as a dependency in your cargo.toml. You can confirm that the crate has been added to your project by inspecting its cargo.toml file. Now, adjust src/main.rs. With your project updated, executing cargo run should set off a few lines in your console. The error is due to the fact that we haven't passed sufficient arguments through to our resulting executable. To pass arguments through, Cargo supports some special syntax. Any arguments appearing after -- are sent through to the resulting executable binary. But Clap does more than provide parsing. It also generates usage documentation on your behalf. Running grep-lite --help provides an expanded view. Section 2.13. Reading from files. Searching for text wouldn't be complete without being able to search within files. File I/O can be surprisingly finicky and so has been left until last. Before adding this functionality to grep-lite, let's take a look at a standalone example in listing 2.27. The code for this listing is in this file. The general pattern is to open a file object, then wrap that in a buff reader. Buff reader takes care of providing buffered I/O, which can reduce system calls to the OS if the hard disk is congested. Manually looping through a file can be cumbersome, despite its usefulness in some cases. For the common case of iterating through lines, Rust provides a helper iterator as the following listing shows. The source code for this listing is in this file. We're now in a position to add reading from a file into greplite's feature list. The following listing creates a complete program that takes a regular expression pattern and an input file as arguments. Section 2.14, Reading from Standard In. A command line utility wouldn't be complete if it wasn't able to read from standard in. Unfortunately, for those readers who skimmed over earlier parts of this chapter, some of the syntax on line 8 might look quite unfamiliar. In short, rather than duplicate code within main, we'll use a generic function to abstract away the details of whether we are dealing with files or standard in. Summary. Rust has full support for primitive types, such as integers and floating point numbers. Functions are strongly typed and require types to be specified for their parameters and return values. Rust features, such as iteration and mathematical operations, rely on traits. The for loop is shorthand for this trait, for example. List-like types are tailored to specific use cases. You will typically reach for Beck of T first. All Rust programs have a single entry function, main. Every crate has a cargo.toml file that specifies its metadata. The cargo tool is able to compile your code and fetch its dependencies. The RustUp tool provides access to multiple compiler toolchains and to the language's documentation. Chapter 3. Compound Data Types. This chapter covers composing data with structs, creating enumerated data types, adding methods and handling errors in a type-safe manner, defining and implementing common behavior with traits, understanding how to keep implementation details private, using Cargo to build documentation for your project. Welcome to Chapter 3. If we spent the last chapter looking at Rust's atoms, this chapter is focused more on its molecules. This chapter focuses on two key building blocks for Rust programmers, struct and enum. Both are forms of compound data types. Together, struct and enum can compose other types to create something more useful than what those other types would be alone. Consider how a 2D point, x and y, is composed from two numbers, x and y. We wouldn't want to maintain two variables, x and y, in our program. Instead, we would like to refer to the point as a whole entity. In this chapter, we also discuss how to add methods to types with IMPL blocks. Lastly, we take a deeper look at traits, Rust's system for defining interfaces. Throughout this chapter, you'll work through how to represent files in code. Although conceptually simple, if you're reading this book, it's highly likely you've interacted with a file through code before. There are enough edge cases to make things interesting. Our strategy will be to create a mock version of everything using our own imaginary API. Then, towards the latter part of the chapter, you'll learn how to interact with your actual operating system, or OS, and its file system or systems. Section 3.1. Using plain functions to experiment with an API. To start, let's see how far we can get by making use of the tools we already know. Listing 3.1 lays out a few things that we would expect, such as opening and closing a file. We'll use a rudimentary mock type to model one, a simple alias around string that holds a file name and little else. To make things slightly more interesting than writing lots of boilerplate code, listing 3.1 sprinkles in a few new concepts. These show you how to tame the compiler while you're experimenting with your design. It provides attributes, like this, to relax compiler warnings. The read function illustrates how to define a function that never returns. The code actually doesn't do anything, however. That will come shortly. You'll find the source for this listing in this file. There are lots of things that need to be built on from listing 3.1. For example, we haven't created a persistent object that would represent a file. There's only so much that can be encoded in a string. There's no attempt to implement read. If we did, how would we handle the failure case? Open and close return bool. Perhaps there's a way to provide a more sophisticated result type that might be able to contain an error message if the OS reports one. None of our functions are methods. From a stylistic point of view, it might be nice to call f.open rather than open passing f. Let's begin at the top and work our way through the list. Brace yourself for a few scenic detours along the way as we encounter a few side roads that will be profitable to explore. Special return types in Rust. If you are new to the language, some return types are difficult to interpret. These are also especially difficult to search for because they are made from symbols rather than words. Known as the unit type, this formally is a zero-length tuple. It is used to express that a function returns no value. Functions that appear to have no return type return this, and expressions that are terminated with a semicolon return this. For example, the report function in the following code block returns the unit type implicitly. And in this example, returns the unit type explicitly. The unit type often occurs in error messages. It's common to forget that the last expression of a function shouldn't end with a semicolon. The exclamation symbol is known as the never type. Never indicates that a function never returns, especially when it's guaranteed to crash. For example, take this code. The following example creates an infinite loop that prevents the function from returning. As with the unit type, never sometimes occurs within error messages. The Rust compiler complains about mismatched types when you forget to add a break in your loop block if you've indicated that the function returns a non-never type. Section 3.2, Modeling Files with Struct. We need something to represent that thing we're trying to model. Struct allows you to create a composite type made up of other types. Depending on your programming heritage, you may be more familiar with terms such as object or record. We'll start with requiring that our files have a name and 0 or more bytes of data. Listing 3.2 prints the following two lines to the console. To represent data, Listing 3.2 uses vec of U8, which is a growable list of U8 single-byte values. The bulk of the main function demonstrates usage, e.g. field access. The file ch3/ch3-mock-file.rs contains the code for this listing. Here is a detailed overview of Listing 3.2. Lines 1 through 5 define the file struct. Definitions include fields and their associated types. These also include each field's lifetimes, which happens to be alighted here. Explicit lifetimes are required when a field is a reference to another object. Lines 8 through 11 create our first instance of file. We use a literal syntax here, but typically structs in the wild are created via a convenience method. String from is one of those convenience methods. It takes a value of another type, in this case a string slice, &str, which returns a string instance. Vec new is the more common case. Lines 13 through 17 demonstrate accessing our new instances fields. We prepend an ampersand to indicate that we want to access this data by reference. In Rust parlance, this means that the variables f1_name and f1_length are borrowing the data these refer to. You have probably noticed that our file struct doesn't actually store anything to disk at all. That's actually okay for now. If you're interested, Figure 3.1 shows its internals. In the figure, its two fields, name and data, are themselves both created by structs. If you're unfamiliar with the term pointer, PTR, consider pointers to be the same thing as references for now. Pointers are variables that refer to some location in memory. The details are explained at length in Chapter 6. We'll leave interacting with the hard disk drive or other persistent storage until later in the chapter. For the meantime, let's recreate listing 3.1 and add the file type as promised. The new type pattern. Sometimes the type keyword is all that you need. But what about when you need the compiler to treat your new type as a fully fledged distinct type rather than just an alias? Enter new type. The new type pattern consists of wrapping a core type within a single field struct, perhaps a tuple. The following code shows how to distinguish network host names from ordinary strings. You'll find this code in ch3/ch3-new-type-pattern.rs. Here is the compiler output from Rust-C. Using the new type pattern can strengthen a program by preventing data from being silently used in inappropriate context. The downside of using the pattern is that each new type must opt in to all of its intended behavior. This can feel cumbersome. We can now add a little bit of functionality to the first listing of the chapter. Listing 3.3, available at this location, adds the ability to read a file that has some data in it. It demonstrates how to use a struct to mimic a file and simulate reading its contents. It then converts opaque data into a string. All functions are assumed to always succeed, but the code is still littered with hard-coded values. Still, the code finally prints something to the screen. Here is partially obscured output from the program. The code so far has tackled 2 of the 4 issues raised at the end of listing 3.1. Our file struct is a bona fide type. Read is implemented, albeit in a memory-inefficient manner. These last 2 points remain. Open and close return bool. None of our functions are methods. Section 3.3, adding methods to a struct with IMPL. This section explains briefly what methods are and describes how to make use of them in Rust. Methods are functions that are coupled to some object. From a syntactic point of view, these are just functions that don't need to specify one of their arguments. Rather than calling open and passing a file object in as an argument, read f, buffer, methods allow the main object to be implicit in the function call, f.read buffer, using the dot operator. Footnote 1. There are a number of theoretical differences between methods and functions, but a detailed discussion of those computer science topics is available in other books. Briefly, functions are regarded as pure, meaning their behavior is determined solely by their arguments. Methods are inherently impure, given that one of their arguments is effectively a side effect. These are muddy waters, though. Functions are perfectly capable of acting on side effects themselves. Moreover, methods are implemented with functions. And to add an exception to the exception, objects sometimes implement static methods, which do not include implicit arguments. Rust is different than other languages that support methods. There is no class keyword. Types created with struct and enum, which is described later, feel like classes at times. But as they don't support inheritance, it's probably a good thing that they're named something different. To define methods, Rust programmers use an IMPL block, which is physically distinct in source code from the struct and enum blocks that you have already encountered. Figure 3.2 shows the differences. Section 3.3.1. Simplifying object creation by implementing new. Creating objects with reasonable defaults is done through the new method. Every struct can be instantiated through a literal syntax. This is handy for getting started, but leads to unnecessary verbosity in most code. Using new is a convention within the Rust community. Unlike other languages, new is not a keyword and isn't given some sort of blessed status above other methods. Table 3.1 summarizes the conventions. To enable these changes, make use of an IMPL block, as the next listing shows. See this file. The resulting executable should print out the same message as listing 3.3. Substituting f3.txt for the original f1.txt. Merging this new knowledge with the example that we already have, listing 3.5 is the result. See this link. It prints the following 3 lines to the console. Section 3.4. Returning errors. Early on in the chapter, 2 points were raised discussing dissatisfaction with being unable to properly signify errors. There was no attempt at implementing read. If we did, how would we handle the failure case? The methods open and close return bool. Is there a way to provide a more sophisticated result type to contain an error message if the OS reports one? The issue arises because dealing with hardware is unreliable. Even ignoring hardware faults, the disk might be full, or the OS might intervene and tell you that you don't have permission to delete a particular file. This section discusses different methods for signaling that an error has occurred, beginning with approaches common in other languages and finishing with idiomatic Rust. Section 3.4.1. Modifying a known global variable. One of the simplest methods for signaling that an error has occurred is by checking the value of a global variable. Although notoriously error-prone, this is a common idiom in systems programming. C programmers are used to checking the value of error NO once system calls return. As an example, the close system call closes a file descriptor, an integer representing a file with numbers assigned by the OS, and can modify error NO. The section of the POSIX standard discussing the close system call includes this snippet. If close is interrupted by a signal that is to be caught, it shall return -1 with error NO set to EINTR, and the state of file descriptor, is unspecified. If an I/O error occurs while reading from or writing to the file system during close, it may return -1 with error NO set to EIO. If this error is returned, the state of file des is unspecified. The Open Group Base Specifications of 2018. Sending error NO to either EIO or EINTR means to set it to some magical internal constant. The specific values are arbitrary and defined per OS. With the Rust syntax, checking global variables for error codes would look something like the following listing. Listing 3.7, presented next, introduces some new syntax. The most significant is probably the unsafe keyword, whose significance we'll discuss later in the book. In the meantime, consider unsafe to be a warning sign rather than an indicator that you're embarking on anything illegal. Unsafe means the same level of safety offered by C at all times. There are also some other small additions to the Rust language that you know already. Mutable global variables are denoted with static mut. By convention, global variables use all caps. A const keyword is included for values that never change. Figure 3.3 provides a visual overview of the flow control, error, and error handling in listing 3.7. Here are the commands that you will need to use to experiment with the project at Listing 3.7. 1. Use this command to download the book's source code. 2. Use this command to move into the project directory. 3. Cargo run to execute the code. If you prefer to do things manually, there are more steps to follow. 1. Cargo new --VCS none global error to create a new blank project. 2. CD global error to move into the project directory. 3. Use this command to add version 0.8 of the RAND crate as a dependency. Run cargo install cargo-edit if you receive an error message that cargo add command is unavailable. 4. As an optional step, you can verify that the RAND crate is now a dependency by inspecting cargo.toml at the root of the project. It will contain the following 2 lines. 5. Replace the contents of src/main.rs with the code in Listing 3.7. See this link. 6. Now that your source code is in place, execute cargo run. You should see output like this. Most of the time, the program will not do anything. Occasionally, if the book has enough readers with sufficient motivation, it will print a much louder message. Experienced programmers will know that using the global variable error_no is commonly adjusted by the OS during system calls. This style of programming would typically be discouraged in Rust because it omits both type safety, errors are encoded as plain integers, and can reward sloppy programmers with unstable programs when they forget to check the error_no value. However, it is an important style to be aware of.